not flat.
Articulation.
Good morning, my name is Krzysztof Bolejko. I'm a research fellow at the University of Sydney, and my field of research is cosmology, and so that's the topic, the subject of my talk today. So I'm going to talk about the curvature of the universe. And before I start, we have to keep in mind that the term curvature is quite ambiguous, and there are many different definitions of what the curvature is, and many people by curvature mean different things. So in order to put everything to a proper frame, I will start with some very basic stuff. So I hope you won't be offended with oversimplified.
We will not be offended.
So I'll start with very simple, oversimplified things, and then I will make things more complicated. I will then introduce the Einstein equations, which provide us with a framework that allows to link the curvature of the universe with other properties of the universe. And then I will show you how we can use cosmological observations to put some constraints on the curvature of the universe. So let's start with the basics. 2 lines. It's straightforward to say which one is straight, which one is curved. The question is, how can we measure the curvature? Because the aim of this talk is to measure the curvature of the universe. So we want to find some practical way we could implement to measure the curvature of the universe. So on this simple example, how can we measure the curvature of this line? Well, there are many ways to skin the cat, but one of the simplest way and one of the most intuitive ways is just to fit a circle. So we can just fit a circle. We know how a circle looks like. We can then take the radius and use this radius as a measure of a curvature.
Well, the difference is, however, that here you are talking about external curvature.
Yeah.
So you must have some other dimension. In universe, you don't have that.
Sure. Yes. So this is a very simple case, and we want, based on that, develop some more practical way that we could use to measure the curvature. Now, just to keep to be consistent with my other slides, in cosmology we usually define the curvature. The curvature has a dimension of units of 1/length squared. So let's add square here, and this can be easily generalized to other dimensions. So for yes.
This picture is a bit misleading.
Yes, it's very simplified.
No, it's not simplified, it's misleading. That's the difference, at least here. Because, I mean, how do you draw that circle?
No.
Okay.
I already mentioned that, and of course this.
Yeah, there's even that. Well, that's the external curvature.
Yes, of course.
So that is clear. But the other thing that is, well, anyway,
Okay, this will become clear, I'm sure, now.
or more confused.
Okay, for 2-dimensional surfaces, we can measure the curvature in different directions and just look for maximal and minimal curvature. And for sphere, the curvature is always the same, just 1/r, so the curvature is 1/r squared. For a cylinder, in this direction it would be 1/r, but in this direction the radius of a circle that you would like to fit here is infinite, so the curvature is 0. And in this case, here the curvature is positive, but in this...
Well, this confusion is even more obvious if you look at the sphere, because these circles or whatever, using the construction which was on the previous slide, refers to the interior of the sphere, not the exterior. Because on the exterior there is infinite number of spheres or circles which touch the point on the surface of the sphere. So that's...
But this definition is...
No, because that's an equation. What is our mean is what is our max.
Well, that's,
Okay.
I mean, if it's defined, if each of these little r's is defined by the construction which was on the previous slide, then for the sphere that can only refer to what sits inside. Because from outside I cannot define, because any circle is...
Well, nevertheless, what I wanted to show is that I wanted to give you a picture of how we could define the curvature.
So how is the r mean defined for a sphere?
Well, they look for great circles and measure the radius of great circles. So the circle that...
Yeah, so that's not this construction from the previous slide.
Sure.
Yes.
Okay, so that's what I'm saying, that the previous slide, that the definition of the previous slide was completely irrelevant.
no, that's not. No.
Okay, but nevertheless, this
In
definition
relation
is
to
still
physics,
quite
right?
impractical because we can't simply use this and measure the curvature of the whole universe. So what I would like to do, I would like to find some other measure that would be more practical and that could give us some better understanding of what the curvature of the universe is. Now, since we can't apply this formula, what other formula could we develop? Well, if we look at other properties of the curvature, we can realize that if we have a vector, and if we parallelly transport this vector to some other place, and then go back to where we started, our vector can be different. Like, for example, in here, if we take the surface of a sphere and just parallelly transport a vector over equator to here, and then to the pole, and then go back to the place where we started, we can see that this is a different vector. So this could be a way to measure the curvature, right? Okay, so let's look at the mathematics. What do we need to know in order to measure the curvature? How would we use this to measure the curvature of the universe? So let's take our vector here at point A and transport it along beta direction to B and then to D. Mathematically, this is represented by this. So this is operation of propagating this vector from A to B and then from B to D. If we do the same but along this line from A to C and then from C to D and take the difference, then we get that the difference is proportional to the vector, but then there's this object here. And this object is known as the Riemann curvature tensor. And this object contains all the information about the curvature that we need. If
But,
space is
this
flat,
difference will also have an addition term.
yes.
Well, depends on
We are
what
simply-
kind of a manifold.
we
If the
assume that
manifold
torsion is
has a
here.
torsion.
Yes, we assume that there's no torsion.
Okay. So this is an additional assumption.
There is no torsion.
Yes, but the point is that we want to be practical. We want to have something that could be practical, that we could implement. We could introduce torsion here, but at the end of the day, we want to take these complicated equations and reduce to the best to one number that we could then compare to observation and measure and say that this is a curvature. So, in that regards, this is a very complicated object. This is a four-dimensional object, so we don't really want to deal with this object. So what we can do, we can actually reduce this object to a smaller object, two-dimensional object, if we just calculate the trace over these two indices. And then we will get the Riemann curvature. And the beauty of this is that the Riemann curvature is involved in the Einstein equations. So we could use the Einstein equations to get some constraints on the Riemann curvature. So these are the Einstein equations. So this is the Riemann curvature. This is the metric, and from the metric we can construct the Riemann curvature. This is the trace of the Riemann curvature. So the left-hand side of the Einstein equations is just pure geometry.
I thought that our alpha beta is Ricci tensor, not a Riemann. Is a
Yes,
big
this
one.
is the Ricci tensor.
Yeah.
So this is the Ricci tensor, which we can get from the
From the Riemann.
tensor. So the Riemann tensor contains all the information about the curvature, but this is a quite complicated object, and we don't really want to deal with it. We want to deal with something simpler, something that could be of practical use. So we reduce this Riemann tensor to the Ricci tensor. And then we can use the Einstein equations, and on the right-hand side, we have the energy momentum tensor, which describes physical processes. So the idea is that if we could use the Einstein equations, we could use some knowledge about the properties of the universe, and then use this to say something about the curvature of the universe. Okay, so let's try to apply these equations to cosmology. So this picture here presents a large structure distribution of galaxies in the universe, of matter in the
In your
universe. This is
presentation, lambda stands for what?
the cosmological constant.
Well, that's what I wanted to know.
This is the
Is it
cosmological
just
constant.
the cosmological constant,
Yes.
or it's the
This is the constant.
density of dark something?
That's the same thing.
Yeah,
There's no
well,
difference.
Reprezentuje
I
jedną
just,
energię.
But for now, let's just assume that this is a
No
constant.
body.
Okay, and let's take the simplest case and assume that the energy momentum tensor is just dust. And this is the standard assumption in cosmology. We assume that all the matter in the universe can be just described by dust. if we take dust, then the energy momentum tensor is of this form. So this is the energy matter density, and this is the velocity field of matter. And then, again, this is a set of 10 equations. So let's try to reduce this even further to a single number. So let's just calculate the trace, and then we will get the trace of Ricci tensor is just Ricci curvature. Trace of metric tensor, that's just 4, because there are 4 dimensions. Trace of the energy momentum tensor is just density. And trace of metric is 4. And there was minus here, so here's minus. So that's our formula, and you can see that the curvature is negative. And if our understanding of cosmic observation is correct, our universe expands. So, and as it expands, its density drops. So in future, this term will be completely negligible. So the curvature of our universe will be just proportional to the cosmic constant with minus. So that's it. That was quick. But let's think about this, and let's think if this is the quantity that we wanted to measure in the first place. Right? We want to have some measurement of the curvature. Well, this was the Ricci curvature, and in 2 dimensions, this curvature reduces to this curvature here. But this is not quite intuitive. This is a curvature of a space-time, 4-dimensional entity. And intuitively, well, it's easier to think about objects that are defined on the surface of constant time, like 3-dimensional objects. So we'd like to have a measure of a 3-dimensional curvature, of a space curvature, that's measure of a curvature of space, not the space time. Well, in GR, we can do that. We know how to project 4-dimensional objects onto the surface of constant time. We can define the surfaces of constant time as we usually do in cosmology, so as a surface that is orthogonal to the flow of matter. We can then project objects onto the surface of constant time and get the Riemann curvature, Ricci curvature, sorry. And if you want to know the details, just go and they are all presented in this paper here.
What's sigma?
Okay, so
Theta?
we know what lambda is, we know what rho is. What about sigma and theta? These are distortions in the velocity field, in the matter field. So there are several types of distortions. The simplest one is where you change the volume but don't change the shape, and that's the expansion. The other type of a distortion is shear, so where you change the shape but don't change the volume. And then another distortion is rotation, where you just rotate an object and don't change the volume and don't change the shape. So theta is expansion rate, and sigma is the shear. So this is the formula for the curvature of space. And it depends on the cosmic constant. That's
What I say is the rho is a property of a matter.
yes,
Lambda is a property of a space,
yes.
right?
No, we don't
No, well,
Consequence
of whatever. That is so to save the letters, I use the space. Now the question is theta. Well, for some reasons omega doesn't enter in this equation
Because in order to define
because
the,
you don't have a torsion.
and not only
Because
that,
these coefficients, sigma and theta, they are some kind of a material properties of that
of
matter.
matter.
Right. Therefore, the way the stress tensor is, which contributes rho here,
Mhm.
is these kinds are the response functions, as we call it in continuous
So in
linear
the
physics,
simplest case,
which measure,
sure.
which measure the reaction of the given physical system to some particular kind of a perturbation. The rho is to the changes of the volume, by the way, so it's not clear whether there is no relation between theta, sigma, and rho.
There is.
Yeah, there is. Well, then therefore they are not independent in this formula, right? And the other thing is that the theta and sigma are related to the properties of the matter.
Sure.
So and the reason why omega doesn't come, that the omega will couple to the torsion.
Not
And
only
therefore
that,
that is like
we had to drop omega when we introduced the comoving coordinates. In order
what?
Co-moving
coordinate. So the surface of constant
There was
time.
an equation which does not refer to the co-UV coordinate, whatever they are.
Well, I could do that, but that it's quite complicated and that would not be very good to produce all the
But my
equations.
question is if the space doesn't have a rotation,
No, we
then
are
how
saying
the rotation of a block of matter can couple to the geometry? This equation, whatever you say, this equation, this one, right?
Well, it
Is
can-
what, I mean, whatever you say is a part of this equation, Einstein equation, right?
Right.
And it says that geometry is related to the matter,
True.
right? Therefore, this next equation tells us that the one of the elastic properties of the system, which is the torsion or rotation, cannot, it does not show up because it cannot couple. There is nothing in the geometry which can couple unless the torsion.
But what you are saying is in accordance with this equation which was written.
Yeah,
There's
that's
no
why
omega in
there
this
is no
equation.
omega, but the question is, why the theta enters independently of rho?
Because it does. I mean, this is a mathematical statement. I don't understand the question. That's
So, okay, after the seminar, I can bring up this paper and then I can show you all equations step by step how we get to this point. The point is that we start with four-dimensional space-time and then project objects onto the surface of constant time. And then, as before, we just calculate the trace, and this is what we get. And we get that the curvature depends on the cosmic constant, on matter density,
It's
shear of matter,
actually the
and
answer is true.
expansion.
Theta and sigma are shear and bulk modulus of this universe. It's elementary.
so it is okay.
No, I just wanted to get the answer.
Okay.
Okay, so we have a formula, and when we apply it, right?
For asking the question.
Well, from this formula we can see that in regions that are rich in matter, like galaxy clusters, where density is quite high and shear can be quite high, and expansion rate is negligible because clusters do not really expand, these terms dominate and the curvature is positive. On the other hand, inside cosmic voids, where density is quite low and shear is also low, but on the other hand, expansion rate is quite large because voids expand faster than other regions in the universe, this term dominates and curvature is negative. So it looks like we are improving. That's the progress. We have a formula that we could use and represent something. Yes.
What about the orders of magnitude? We can roughly estimate the value of lambda and rho. How does theta and sigma compare when you put numbers here?
Okay, if we put numbers, then this term is smaller than this one, but this one is comparable to this term. If we, okay,
But what about lambda? Because lambda is also crucial here. If you want to say curvature is positive or negative, the lambda is
The
crucial.
lambda decides, right?
true. So you can also estimate lambda from other types of cosmic observations. The point is that still this formula is not really practical for us because we can't really send astronauts to different places in the universe and tell them to measure these quantities and then come back to Earth and report what they measured. So again, we want to find something better, something that could be practical. Okay, so we would like to know what's the average curvature of the universe, that's for sure. So the question is, if we could calculate the average curvature, would we get something positive, like in regions of high density, or negative, like in voids, or would we get that positive curvature of clusters is compensated by negative curvature of voids, and we get zero at the end?
But average means
Volume average.
But well, so if I choose a proper volume, it's flat.
Why?
Well, because anything average and proper
No.
is
That's not.
Well,
Why?
The surface of the sphere is always curved, independently of the...
Well, you take, for example, a cluster, right? Let's take a cluster. I know what's the volume of
But
this
I
cluster.
understand this is a curvature for the whole unit.
Yes.
Yes.
So we can then expand this
And
further.
we are
and-
not talking about the local quantity R cubed, R3. Because, I mean,
No. Locally, it may vary, but if
Yeah.
you would like to know some average.
Yes. So we'd like to know some
but
average
over what of the whole universe?
of our whole universe, of our whole observable universe. Now the point is
But
that
I have a question because
Sure.
at the beginning you assume that everything is homogeneous, yes?
Yeah.
Because this
no,
energy moment tensor
No, it's not homogeneous because we
was
have
position
electrons.
independent, but this T is position independent.
no, this row can be position dependent. There's no assumption
Okay.
about this are homogeneous. We will eventually, well, okay, that's a good point because still, in a real case, we can't really employ our formula and get the value of the curvature. But what we can do, we can assume that we can take homogeneous models and try to find the best homogeneous models that fits the observational data the best, and then using the properties of this homogeneous universe, get the estimate on the curvature. And then the question is how these two quantities relate. But I will focus on this later on. Let's just see what would we get if we just take a homogeneous universe and calculate and use the properties of a homogeneous universe and cosmological observations analyzed within the frame of homogeneous models. What value for R would we get? Okay, so this is the standard cosmology. So before I'll show you the constraints on the curvature, let's bring all our assumptions just to be sure that we know what we are measuring and we have a clear understanding of these constraints. So the first assumption of standard cosmology is that we can apply general relativity. So here are the Einstein equations. Then the second assumption is that the universe is homogeneous and isotropic. Because in general case we can't resolve these equations. If we assume that the universe is homogeneous and isotropic, we can simplify these equations and solve them. The metric of a homogeneous model is here, and it's very simple. There's only one function of time and one constant. So this is all we need to know in order to define the metric.
So the A and K are given in terms of the sigma, theta, and rho.
Not yet. They can be expressed in the,
They have to be expressed.
yes. We will get to this point later on. This is what we would like to do. We would like to express curvature. Well, I'll show you later on how K can be related to and A can be related to curvature, and how
So in other words, is this equation a solution of the Einstein equations
Yes.
for some sigma, theta?
Yes, Robertson.
That's what.
May I
Walker
comment? There is a fundamental problem of cosmology because we know that the universe is not homogeneous. There are some stars, and we would like, on the other hand, we would like to view the universe as
It's a soup.
some average.
Soup.
Yeah, and this is a tremendously difficult problem, and as far as I know, nobody has defined the procedure of this. How to?
Kaczynski is working on that.
Yeah,
That's what
he's
I was
working
about
on
to
that.
say.
Many people are working on it. I was working on that 40 years ago. In any case, this is a very difficult problem, and I understand that you are trying to present one of the approaches, one of the possible approaches. How to average in general, how to define averaging procedure in general relativity. It is by no means well defined.
Yes, this is a very
Uniquely, probably. It's not unique.
So we know how to deal with this. Like we know how to deal with homogeneous models, how to evolve homogeneous models. But we don't really know how to deal with this, how to deal with the real universe. So, and the question of the curvature will pop up later. Because the point is that we can always average everything in our universe, like the matter distribution of expansion rate at some given time. We can also do that at a later time. The question is, does this average correspond to the same homogeneous model as the average here? It may not.
Well, of course, equations are highly nonlinear, and it's very much everything depends highly upon what do you want to average.
And this is one of the motivation behind this talk is that we can use curvature as a tracer of that, because the curvature here can be expressed in terms of some constant, which in the homogeneous models are just constant. So you can express the curvature in terms of a constant that does not change. So the curvature should remain the same in this case, but in this frame it can be different. So if you could measure that the curvature changes, that would be a strong point that we can't really do this procedure and replace a complicated system like our universe with homogeneous models. But we will get to that later on. Let's first start with the simpler case, and let's start with an assumption that the universe is homogeneous or can be expressed and modeled using homogeneous models. And let's try to use cosmological observation to put constraints on the curvature and see what value do we get. Okay, so first we assume the Einstein equations, then we assume that the universe is homogeneous and isotropic, and the curvature is related to these two quantities. So the curvature of a space is just a ratio of the k over a squared. And this k is a constant, and this function here can be rescaled. So by curvature now, when referring to the curvature, I'll be referring to this index here. So what's the value of this k here? Now the good part is that besides geometry, we also have physical processes. We also have properties of the universe. And we can use these, and in combination with the Einstein equations, we can put constraints on the curvature. So instead of, okay, so we know the left-hand side. As for the right-hand side, we will assume again that the universe is homogeneous and it's just dust, and we will have two fluids, cold dark matter and baryonic matter. And omega is just a dimensionless quantity. It's just a ratio of the matter density today to the critical density. Or, as you can see from here, this is just a matter density multiplied by some constants. And the good way of the reason why we're doing this is that this dimensionless quantity of order of between 0 and 1. So it's easier to work with this quantity than with matter density. We can do the same scaling for k and express k in terms of omega k. And again, this is a dimensionless quantity of value between 0 and 1. And the same with lambda. We can express lambda in terms of omega lambda, which is again lambda multiplied by some constants. So now the point is that we would like to use the Einstein equations, the evolution of the universe, and get to know the properties of the homogeneous model, and using these equations and all the other quantities to put constraints on the curvature of the universe. Now the point is that our universe is not homogeneous. There are inhomogeneities. So in the standard cosmology, we allow for inhomogeneities using perturbations. Usually they are just linear perturbations, and you find perturbations as
A światło jest?
Prądu chyba nie ma.
Na stacji było.
Nie ma prądu.
nie szkodzi, można użyć tablicy.
A panią też wyłączyli.
Ma tą baterię wbudowaną, więc jeszcze przez jakiś czas podziała.
Komputer też ma.
A przewidywali,
Ale rzutnik już nie.
Połączenia dopiero w 2016.
Przy 20 stopniach zasilania.
Unfortunately, I had some slides that showed were meant to show you how we could use cosmological observations to put some constraints on other properties of the universe, and then from these properties of the universe get some constraints on the value of the curvature.
On też jest elektryczny. Nie, on jest też elektryczny.
A może to korki?
So,
Może karty. Damskim.
Dobrze, że nasze krzesła nie są elektryczne.
Wiem, ale nie trzeba.
I'm just thinking how to lead, how to proceed further without my slide. Okay. So the idea is to use cosmic observation to put constraints on some different properties of the universe, and then use this to say what is the curvature. And if you do that, and you can get that the curvature is zero. It's with accuracy of a few percent is consistent with being zero. And the tightest constraints come from the cosmic micro background radiation, which is the radiation that was emitted when the universe was young. So if we do the diagram, time, space, and this is how light propagates, we can use different types of cosmic observations. So we can use observations around our galaxy, for example, how things expand, how the universe expands, how the global universe expands. From that we can get the Hubble constant. From the distribution of galaxies, we can get constraints on omega matter, on the amount of matter in the universe. From the observations of supernovae that are much further, and supernovae are stars that explode, and they can be used to estimate the distance quite accurately, we can get constraints on omega matter and omega lambda together. And then the tightest constraints come from the cosmic microwave background. So this is when the universe was very young, roughly 5,100 years after the Big Bang. And from the observations of cosmic microwave background radiation, we can get the tightest constraints on our cosmological parameters. And if we combine those together, we can get that the curvature expressed in terms of the dimensionless quantity omega k is more or less zero, with the accuracy of a few percent. And actually, well, some would say that this is what is expected, right? If we had inflation in the early universe, inflation should leave the universe quite flat. And since in the homogeneous models, omega k, this quantity does not evolve, it should stay flat. And this is what we can see, especially when we look at the cosmic microwave background radiation, that the universe was quite flat when the cosmic microwave background radiation was emitted. Now the question is, does this quantity remain constant, or does it change? If the universe can be described using homogeneous and isotropic models, then no, this quantity should be constant. But as we mentioned before, our universe is quite inhomogeneous, and with time, inhomogeneities evolve and grow. So if we calculate averages at different times, we can get different homogeneous models, and therefore the average curvature could evolve. So how could we use it? So how could we measure this quantity? So from this picture we see that we should rather try to measure the curvature, not here when the universe was very young and very homogeneous. We should try to measure the curvature in this region here, where structure, when they are quite evolved and when the universe is quite homogeneous. Okay, so this brings us back to where we started.
May I
Yes?
have a comment? So you may draw the following diagram, that you perform averaging procedure at one instant of time and another instant of time. Now, if the evolution, the true evolution is governed by the Einstein equations, then the evolution of this average space-time is no longer governed by Einstein equation, because averaging is not
Covariant.
they are not non-commutative, one can say, yeah? Averaging and
Well, I would say it is still covered by the Einstein equation, but a different equation, because
by the different equation, because when the equations are highly nonlinear, the averaging procedure does not commute with the evolution. This is the problem.
This is very similar to Ehrenfest's theorem from quantum mechanics. Only for linear systems.
Yeah, only for linear.
so from the theoretical point of view, this is quite a complicated problem, and there's still no solution for that. And so I would like to approach this problem more from the more practical point. I would like to say, okay, in a homogeneous case, this quantity does not change, but in a general case, this quantity should change. The question is, can we measure this change? So this is. So how could we measure this? Well, one of the implications of curvature is that, for example, if we have a triangle, and if you take angles, the sum of these angles should be just 180 degrees if the space is flat. If the space is not flat, the sum of these angles can be different. Again, you cannot take a triangle like this in the universe.
Z ostatnim życzeniem do tego.
But I would like to suggest a different triangle than that. And this is a triangle that we can actually have in the universe. So, and for that we can use gravitational lensing.
We could also call it a straight line.
Yes. But the point is that we know this distance here, between A and B. We know the distance between C and D. And we know the distance between A and C. And this is what we can measure. Using the gravitational lensing, we can measure the distance between lens and observed galaxy. We can measure the distance to the lens, and we can measure the distance to the observed galaxy. So this is what we can measure, and this is also in the region, the space that we are most interested in, here in the late universe. So during my talk, I wanted to show you how we can use gravitational lensing and also supernovae observations to get these distances and get the constraints on the curvature. Because if you write down the equations, you can actually see that you can express the curvature in terms of these distances alone. So, to cut things short, let me just show you the constraints. So the probability distribution function, if we use the observation, the present data, and measure those distances and get the constraints on omega k, the constraint would look like this. So 0 is consistent and the margin is quite broad. The point is that we have very little lensing data. we have only 30 galaxies. If we could have 30,000 galaxies, then we could reduce these constraints to the constraints of order of 2%, or 0. We could reduce the width of this curve to very, very small value, comparable to the constraints that we get from cosmic macro background radiation. The beauty is that this would be the constraint on the curvature in the late universe, and in future we will have enough data to produce this tight constraint. And by future I mean in 2020 Euclid satellite will be launched, and it is estimated that Euclid will measure gravitational lensing for more than 10 or 20,000 galaxies, and the same with supernovae observations with dark energy survey that is currently measuring supernovae. We will have by 2020 something like 20,000 supernovae observations.
Can you explain in some more detail how is lensing related to these observations?
So lensing allows us to get this, say, in quotation triangle. From lensing we can get the distance, we can get the ratio between this distance here and this distance here. And then using supernovae observations we can get the distance from here to here and from here to here. And then if we combine those distances,
A bit more.
Sure.
How come that from lensing we get this distance?
I just use my slides because I have a formula up there.
Powinniśmy kupić sobie takie generatory minerowe. Zapuściłoby się i...
If we write down the formula for the distance redshift relation,
Że taki nie.
Chyba pierwszy raz od 20 lat na taką powiedzieć.
Co mówisz?
Chyba pierwszy raz od 20 lat. Taki blackout.
Mnie się wydaje, że w ogóle pierwszy raz w ogóle w historii.
Nie, w 80
Poza tym to jest lokalne, bo zegar chodzi, w związku z tym część
Zegar jest na baterii.
na baterii.
Bakterii. Zegar ma bakterii.
so
Zegar jest bakterii.
this is the formula for the distance redshift relation, and it depends on the curvature. Curvature is here under the integral. It's the same hyperbolic sinus. The curvature is here. This is the expansion rate, and this is also the expansion rate that depends on the omega mater, omega lambda, and other terms. So the curvature is quite involved in here. But because this is a hyperbolic sinus, we can use some geometrical, mathematical.
Where does this come from? What is the...
So this is the standard distance redshift relation.
I know
Yes.
you say it's standard, but where does it come from? What
To
is
jest standard textbook. To jest standard textbook.
So this equation tells us how to calculate the distance to a galaxy of a given redshift. And the way to
So this is a geometrical relation,
yes,
taking into account the
yes,
expansion
true.
and z is direction. But why is this?
Na razie nie ma w ogóle wzoru.
Yes, there is.
A,
The formula.
So do you want me to derive this formula?
No, perhaps that would be.
we don't have enough space on the blackboard.
But the point is that using some simple geometrical relations,
Intuitively, what makes it strange is that you integrate over all redshifts.
well, to the redshift where the galaxy is located. So we are here. We,
Yes, we are here, and the supernova is over there.
and there's a redshift some. So
This is the actual redshift for the supernova. Where does the integration over all the redshifts come from? That the signal is traveling and then you integrate, and in the meantime the Hubble constant changes.
true. Well, we can get this from the metric.
And don't write,
No?
Why not?
because we know this.
No, we don't.
Oh, you see.
Non-seminarium.
So we take now geodesics. So this is just 0. Well, it was plus. So one over ace dt equals dr 1 minus k r squared.
Yes, and then you integrate
So we integrate time r. Here's how light propagates. Here's a galaxy. So we need to integrate over. And then we use a trick where we replace time with redshift. Because the redshift, this is what we can measure.
That's right.
And that is why we have the
Right, in fact, you have the distance and here.
yes.
Okay.
And because of A and transition from the time to redshift, we get the expansion rate. And now we can actually see.
But there's no lensing involved here.
Not yet, but we can do this. This is from
This is
from us to the source, but we can also do the same between lens and the source, and then it will be the same. It's just that the redshift will change. And now the beauty is that if we combine these equations and using some simple mathematical identities, we get the following formula. Okay, so looks quite complicated, but the beauty is that we now, this formula is no longer depends on the expansion rate, no longer this depends on other quantities, it's just omega k and distances. And these distances can be measured.
How do you measure the distance in the opposite direction? I mean, from us to
So this is the observer, here's lens, here's some source galaxy, and because of lensing, we can measure this ratio.
this is where lensing comes.
This is what the lensing does. And from supernovae observations, we can get the distance dl and ds. So using lensing and supernovae observations, we can get dl, ds, and then this ratio. And then here is a pure mathematical formula for the curvature. And the beauty of this formula is that it just depends on distance, something that you can measure, and there's no assumption about the expansion rate or dark energy. just geometry. And right now, if we use this formula, the constraints are not very tight because we only have 30 lensing systems. But in 6-7 years, we'll have 30,000 lensing systems, and the constraints will be comparable to the constraints that we get now from cosmic micro background radiation. And so the hope is just to see if the curvature is still consistent with 0 or if it's some other value. If it's, we should expect to see some other value, but we'll see.
So the great advantage is here that you don't use any averaging, anything like that, just measure it. Just take the observations.
Just as empirical.
This curve was from here.
Yes, the probability distribution of
Even present data.
present data.
That is why it's so broad, because of the errors.
The constraints is like this, and we did simulations that once we had 30,000 lensing systems and 20,000 supernovae systems, then we will be.
And it will not be, are you sure that it will not be shifted?
Well, in simulations we assume that the universe is flat, but if we can assume that the universe is not flat, then. But the point is that in the future we will have a much tighter constraint. So that was my talk.
Now it's asymmetric.
Yes, it is asymmetric. It's not symmetric. It's
So it
asymmetric.
rather
It's skewed.
indicates that the current is positive.
True.
Thank you.
No, omega k is positive. Curvature is proportional to minus to omega k. So the curvature is negative.
Curvature is negative because omega.
Yes.
Thank you.
Thank you.
Thanks with apologies from local power station.
Ciągle jest wygaszane.
Yes, it's not clear because in other buildings the lights are on.
Maybe
our colleagues, experimentalists have done something. Maybe.
they have measured.
Any questions?